we're going to test every power series as though it were a geometric series. And if the power series behaves geometrically, then we can find the interval of convergence. Let me tell you what I mean. So when we're looking at a geometric series, in order to find the ratio from one value to the next, we would take the next term in the series divided by the term before it, and that would give us that common ratio, what we're multiplying one term by to get to the next. If we can do that for any power series, then we would know that the power series will converge as long as the limit as n approaches infinity of the absolute value of r is less than 1. Or, in the situation that we just looked at, as n approaches infinity of the next term divided by the previous term is less than 1. And we know that a power series would diverge if the limit as n approaches infinity of r is greater than 1, or if we put in what we know, that to find r, it's the next term divided by the previous term, if that's greater than 1. And inconclusive, so what would happen if that ratio is equal to 1? That means it's not behaving geometrically. That would mean this power series does not behave like a geometric series, and this test is inconclusive then. So if we take the next term divided by the previous term and we get 1, not a geometric relationship in these terms, so we can't tell. We don't know. All right, here we go. Let's do some algebra. I'm going to go as slow as I can so that you can understand what's going on. So here's our first power series. We're going to use the ratio test to determine convergence. If the series converges, then we'll determine the radius and the interval of convergence, and that'll just happen naturally. Okay, so let's take a look at this. In order to figure out if this behaves geometrically, we need to know the next term and the previous term. In other words, we need to figure out what is a sub n plus 1. A sub n we know already. A sub n is just this term. Like that. The next term would be all of these values to the n plus 1. So this is n plus 1 factorial. We're looking at the next term in the series. In order to determine if this will, I'm going to use a different color now. In order to determine if this will converge or what this will converge to, we need to find the limit as n approaches infinity of the next term divided by the previous term. We're taking the absolute value because we don't care if we're multiplying by a positive or a negative. We're saying we just need to know if this limit is less than 1 or not. All right, so here comes the algebra. We need to do some division here. So first things first, in the numerator, I'm going to write this out as, I can't lose my limit. Don't lose your limit as we go. I'm not going to have enough room. I'm going down to the next line. Okay, I'm going to rewrite the numerator. As 2 to the n times 2 to the first n plus 1 factorial is n plus 1 times 1 less than that, times 1 less than that, and so on. X minus 1 to the n plus 1, I'm going to do the exact same thing, and I'm also going to put this on the top to make life easy on us. X minus 1 to the n times x minus 1 to the first. I squeezed that in here for no reason. Let me go back to this and make sure you understand it. So n plus 1 factorial is n plus 1 times 1 less, times 1 less, times 1 less. Okay, the denominator, you know what, I'm going to save me some steps because this takes so long to write. The denominator, when we divide two fractions, I'm going to flip the denominator and multiply. So I'm going to flip this over and multiply. So I'm going to move this x minus 1 to the n to the numerator to make it easier to do. So now when I flip this and multiply, it's going to be easier to make that happen. So when I flip it and multiply, this now becomes n factorial, which is n times n minus 1 times 1 less times 1 less times 1 less over 2 to the n times x minus 1 to the n. The reason why this is all helpful to simplify it like I did is because now you can see that things are going to start to cancel out. For example, this 2 to the n and that 2 to the n cancel each other out. X minus 1 to the n and x minus 1 to the n cancel each other out. This n cancels with that, which cancels with that, which cancels with everything else after it. So what we end up with then, after we've done all of this simplifying, remember we haven't even found the limit yet. We're still carrying that along with us. So after simplifying this, I end up with 2 times x minus 1 in the numerator and n plus 1 in the denominator. Okay, now that I have this simplified out, I'm going to take the limit of this as n approaches infinity. And remember, x is just some x value that we're going to plug in, like 1.5 or 1.347. N is approaching infinity. So as n approaches infinity, that means this denominator grows very, very quickly, and the numerator is very slow. So that means this limit, this thing, approaches 0. Remember the criteria. If the limit, as n approaches infinity, of the next term divided by the previous term is less than 1, then we know that this thing converges. So, since this turns out to be 0, we know that this thing converges. Since 0 is always less than 1, this converges for all values of x. In other words, it doesn't matter what value you put in here for x, this limit will always equal 0. So the interval of convergence in this case is negative infinity to infinity, and the radius of convergence is infinity. Okay, let's try another one. I'm going to give you a shot at this. I want to see if you can write the limit, if you can find the next term over the previous term, see if you can do the algebra, and we'll come back together. Okay, I hope you actually tried. So if I look at the next term, this is negative 1 to the n plus 1. Here's where people mess up if they're going to mess up. This is replace n with n plus 1. So I'm replacing n with n plus 1 over 2 times n plus 1 plus 1. Okay, when I find the limit then, as n approaches infinity, remember I'm finding the absolute value. So the negative ones, the absolute value of those will become positive anyway. So I'm going to not rewrite those negative ones because I'm taking the absolute value of this. Okay, so I've got the next term, which is 2n plus 2, and then plus one more, so this is 2n plus 3, and then we have 2n plus 3 in the denominator, over the previous term, which is x to the 2n plus 1 over 2n plus 1. I'm going to rewrite this just over here because I've got space in this case. I'm going to flip the denominator and multiply. So I'm going to rewrite this as x to the 2n times x cubed over 2n plus 3 times, and I'm going to flip the denominator, so I have 2n plus 1 over x to the 2n times x to the first. So I just split this up into two parts, and I split that up into two parts as well. Now I can see that things will start to cancel each other out. X to the 2n, x to the 2n. One of these x's will reduce, so this x will take out one of those. So I've got x squared. Here's where I'm at now. After I do all of this simplifying, I've got the limit as n approaches infinity of x squared times 2n plus 1 over 2n plus 3. Okay, remember, we're looking at the limit as n approaches infinity. N approaches infinity. So the plus 1 and the plus 3 are inconsequential. They will not affect the growth of n at all. What we're looking at then is that we've got 2n is growing at the same rate as 2n. So as n approaches infinity, this approaches 1. What we end up with then is x squared. Not sure what that's going to do for us, so let's keep going. To determine if this converges or not, we know that the absolute value of r must be less than 1. Now we can't just do what we did in the last video. We cannot just say always, in this case it's going to work out, but we can't just say, oh, well then this must be negative 1 to 1. In this case it works out because it's just x squared, but if we had some different function here, like if it was x squared plus 5, completely different story. What this is saying is on which values of x is x squared going to be less than 1? So let's look at the graph of x squared. Here's 1. On which values is that parabola going to be less than 1? And in this case, it does happen to be negative 1 to 1. It will not always be. If you had a different quadratic, this would be a totally different story altogether. So what we know then is that when x is between negative 1 and positive 1, the parabola is less than 1. All right, so we just found our interval of convergence. The interval of convergence is negative 1 to 1 as far as we know. We don't know about the endpoints. We'll look at that later. And the radius of convergence will also be 1 because the center is at 0. All right, that's the beginning of our conversation for tests for convergence.